Okay, so here's a video. We're going to look at an example of an electrolysis reaction, and we're going to write a comprehensive overview of this electrolysis reaction. So in this electrolysis reaction here, I have a crucible. Okay, so this shape here is a crucible on the left, and it's full of zinc iodide. Now here I've got a wee subscript to say it's a liquid. Now the reason it's a liquid is because this is molten. Okay, and I can see two observations here. There's some bubbles here, some gas produced on the left hand side, and then purple gas, and there's grey liquid produced on the right hand side. But what is it we have to write for a comprehensive explanation? So the first thing we have to do is look at the reduction potentials and work out which one is going forwards, has been reduced, and which one has been oxidized. Okay, then we have to link these observations we have on the left to the reactions that we write. I have to justify at which electrode is oxidation or reduction using loss of electrons or gain of electrons. I also have to justify using oxidation number changes. I then need to take the two equations I have and write them, make sure they're balanced and put them as a full equation. And I have to calculate the potential of this electrolysis cell. How much voltage is needed to make this reaction happen. And finally, I'm just going to put everything together and say what this comprehensive overview means. Okay, let's get into it. So we can see the observation here at the cathode here at the right hand side. We can see that there is a pool of silver liquid formed around the cathode, and we can see purple gas is happening at the anode. Let's go up and look at these redox couples because I'm kind of interested. What is this purple gas? Okay, so the purple gas, it's not going to be the two ions. Okay, so it's either going to be zinc or iodine. Well, zinc is obviously going to be the silver liquid. Now, why is it liquid? Well, because this crucible is heated, and in here is a liquid solution of an ionic compound. So it's got to be quite hot. So as soon as the zinc metal is made, it actually becomes a liquid. Same with the iodine. Iodine would be a solid at room temperature, but as soon as it's made, it's going to turn into iodine gas. So these are the things that we can observe here. Which one of these is going to be reduced? Because this is an electrolysis reaction, this is different to an electrochemical or galvanic cell, which produces energy. This needs energy to make the reaction happen. I need to supply electrical energy. So actually, in this case, the most negative redox potential goes in the way that it's written, because energy is provided, right? So overall, we're going to get a negative energy from this cell. So I need to write, so I'm going to write the zinc to zinc, zinc plus to zinc going forwards. The other thing that I might notice from this is that because this is made of zinc iodide, which means if I look at this yellow box up here, zinc iodide liquid, it's made of zinc ions and iodide ions. Those are the only two things that we can start with in this solution. So you can actually say, even though we know it's the most negative, so it goes forwards, the other reason for this is, look, there is no zinc metal at the start, there's only zinc ions, so that must be the reactant. And there is only iodide ions at the start, so that must be the reactant for the other equation. Anyway, so I've written this down. Cool. Let's explain whether it's oxidation or reduction using the loss or gain of electrons. We can see here that there are two electrons on the left. It is gaining them. So this is going to be Leo, the line goes GER. That's how I remember this. Leo, which is LEO, loss of electrons, oxidation, GER, gain of electrons, reduction. This is gaining electrons, it's reduction, but let's be specific. The 2+ ions are attracted to this negative electrode. Why? Because they're positive, this is negative, they move towards it. When it gets to the negative electrode, they gain electrons from it. This is giving electrons to the 2+ ions. Each zinc gains 2 electrons to become zinc solid, which is observed as a silver liquid around the electrode. It doesn't join to the electrode in this case, remember, because the actual solution is a molten solution of ions. It's really hot, so as soon as the zinc metal's made, it actually is a liquid. Let's explain using oxidation numbers. Okay, we'll put those down there. +2, this monatomic ion, It has a charge of 2 plus, so it's plus 2. Then we have this metal on the right. It is an element, so it has an oxidation number of 0. 2 plus 0. The oxidation number is reducing. That agrees with what we said in the other one, so we can say that the zinc 2 plus, the species that is the reactant here is reduced as the oxidation number of the zinc atom that is part of both the zinc 2 plus and the zinc metal decreases from plus 2 when it's a zinc 2 plus to 0 when it's in zinc liquid. Okay, cool. I'm happy with that. Let's take the other equation. So looking up here, remember the yellow here, the zinc iodide is actually made of iodide ions. So we're going to start with iodide ions and we're going to go to iodine. Here we go. So when I balance this, now be very careful about balancing these equations. It's very easy just to miss that there are 2 iodines here. So you have to put a 2 in front of the I here. The other thing that people often make a mistake with is they do not write 2 electrons here. They just put 1 because they see the -1 charge. Take care when balancing this equation. Okay, let's explain it using loss or gain of electrons. So this is losing electrons. Leo goes grr, so this is going to be loss of electrons, oxidation. So the I ions are attracted to the positive electrode. So this is the positive. See this? It's here. This is the anode. Now the reason this is called the anode is because oxidation is happening here. And the other electrode that's negative is the cathode because reduction is happening there. So oxidation is happening here. It's positive. The negative ions are going to be attracted to it. And when they get their electrons ripped off them by the power source so they can give them to the zinc. Okay, so this power source here is ripping electrons off the iodide ions and pumping them through and giving them to the zinc ions so they can become zinc metal. So the iodine ions are attracted to the positive electrodes. 2 iodide ions lose a combined total of 2 electrons to become I2. Notice I've given the exact ratio of the ions to the electrons to the molecule here so that I can be detailed enough and I can get a good grade in my achievement standard 91393. Because of this, the I2 is purple. Purple I2 will be given off at the positive electrode. And in this case, remember this is the anode. We can also explain it using oxidation numbers. And I minus is an oxidation number of -1. Because it is a monatomic ion and it's equal to its charge, and I2 oxidation number of 0 because it is an element. We can see the oxidation number goes from -1 to 0. It's increasing oxidation. That agrees with our loss of electrons. So the I minus is oxidized as the oxidation number of the I atom that is in both of these, the ion and the molecule, increases from -1 in I minus to 0 in I2. And here, this is the explanation of these equations, the reduction and the oxidation equations, using both a loss and gain of electrons and change in oxidation number. I've also justified at the top here why we said that the zinc ion to zinc metal is the reduction in the first place. Okay. Let's have a look at balancing these equations. So remembering that we had these 2 half equations here. Oh, wow. Okay, looking at these 2 half equations, this is going to be more straightforward because I can see here right now that there are 2 electrons on the left and 2 on the right. So what I'm going to do, cancel those and just write down the full equation. I don't need to multiply any of the equations here because the electrons being gained and the electrons being lost are balanced, so I just add them together and cancel the electrons out using our linear algebra. Okay, awesome. Now what we want to do, that's our fully balanced equation. Not sure why they make that an excellent skill for the standard, but hey, well, let's do the E cell calculation here. So, or the E calculation, not an E cell. So the E calculation here is we are going to take the reduction electrode and we're going to minus the oxidation. So there isn't a left-hand cell and a right-hand cell like the galvanic cell. So here, which one was being reduced? Oh, it's the zinc. Cool. And we're going to subtract the one that's been oxidized, and that is the iodine, right? So we're going to go minus 0.77 minus positive 0.56. Now, when we minus a positive, that just becomes a negative overall. So we're going to get negative 0.77 minus 0.54, and our answer is negative 1.31 volts. Amazing. We're really happy with this. This is an electrolysis reaction, so we know that the E value is going to be minus 1.31. That means this reaction is not spontaneous. This will not happen by itself. If I have molten zinc iodide, it will not undergo this change. It will only undergo this change if I stick 2 electrodes in that have electrical energy going through them, okay, connected to them, because the electrical energy have to rip the electrons off the iodide and then give it to the zinc. It needs to make a reaction that wouldn't happen. So this is a non-spontaneous reaction, and we know that because the E naught value is negative. So this reaction is not spontaneous, and electrical energy is required to make it happen. That's the final statement. I need to make sure that I just finish off this report, this explanation, to get my excellence. I hope this has helped you with unpacking electrolysis, what it is and how we can explain it. Look out for my next electrolysis explanation video.